In this video, I'm going to give you guys an overview of how scheduling is done on multiprocessor systems. Now we're going to talk about things at a very high level. Obviously, right, this can be kind of a very complicated topic. So first thing to note is we have two general types of systems. First one's called asymmetric multiprocessing system, or a SMP, or symmetric multiprocessing system. So AMP and SMP. Usually people use the acronyms either AMP or SMP. So how these two things differ, right? So these are two schemes for controlling basically how do I assign work to different processors. In an asymmetric scheme, what happens is I have one CPU that's basically in charge of everybody else. So I send all my jobs to this one CPU, and the CPU says, oh, you know what? I see core 2 is free and core 3 is free, so I'll send them jobs. I see core 4 is busy, so I'll leave them alone, right? So I have one CPU basically in charge of managing all of the assignments of processes to different CPUs. Second thing I could have, right, is a symmetric approach. In a symmetric approach, maybe there is basically just one big basically pool of processes out there, and every CPU looks at that pool and takes stuff and like runs with it. So instead of being, having one person basically in charge, it can be like, oh, this process needs to do this process needs to do this. You have basically everything kind of broken up, right, so that CPUs really are independent, right? They kind of just grab whatever it is they want, right, and then they're able to do their processing. So the question here for you guys, right, is which of these is probably more reliable? So maybe take 1 second to think about that. So here I would probably opt for, well, here we have kind of things that go back and forth. And it depends also a little bit how much you trust your hardware. So if your hardware is a little bit untrustworthy, probably SMP is going to be what you want. The reason there is that if you have a CPU fail, right, it happens to be your one CPU that's in charge of assigning processes, well, that'll basically doom the system, right? So if I have a kind of this mistrust of my hardware, AMP won't really do it right. If I'm on SMP, right, then maybe it'll be fine, right? In that case, basically, I know that the other processor will basically just keep on running independently. They won't be impacted at all. If I'm pretty sure that my hardware is good, maybe then we're worried about software issues. Maybe asymmetric is better, because in that case, I have one person in charge of task assignment, right? So I don't have the issue with two CPUs, trying to go and grab the same thing at the same time. There's just one process, right, that's allowed to do that management, right? So maybe from that standpoint, I would pick the AMP or the asymmetric model, right? If I care about preventing software issues, right, versus hardware issues, more for for symmetric processing can kind of address that. Okay, so in general, what a scheduler is trying to do is match up tasks to processes, and that's just about it. Now, we have to basically be a little bit careful here, though, because what happens is that when we think about, let's say I have basically a system, right? So I have, basically CPU 1, CPU 2, and I have, maybe CPU, 0, CPU 0, right, is running something, CPU 1 is running something. Let's say this is, P0 over here, P1 over here. Then maybe things change a little bit, right? I have, all of a sudden I have, basically, P2 is running over here, right? P2 is also running over here. Well, let's see the P1 over here, right? So this process over here, right, was basically running P0 before. Let's say I stop P0, now I'm running P2. And in my back of my head, I actually had to keep in mind a second thing, which is there is some sort of a catch, right? The catch is like the data that's available to the CPU. And so all the processes that CPU is running at a given time might exist on this catch, right? So maybe P0 is there, P1 is there, P4 is there. Let's see. Actually, we shouldn't do P1 because P1 is not a different processor. Let's do P3. So let's say I have those, P0, P3, P4. Those are all on the catch for CPU 0. CPU 0 is now running P2. Now, if basically I'm asked to run, P0 again, right? I always one that I started with, let's say I'm asked to run it again. It would be ideal for me to put on this processor 0, right? It would be ideal for me to redo, P0 is here again, right? And then, kind of P2 goes back to that catch. I don't want to put it over here, because this CPU over here will have a different catch, and this different catch is different process. So maybe it has P0, P8, P9, right? So even if both of these are free, and I'm trying to schedule, my P0 again, right? I have a choice, right? Do I want to put it on this process 0, right, which is running 2, or I put it on this process 1, which is running process 1? Well, what I want to do is I want to put it on this one, right? I want to put it basically on, and this should be, this is the 0. I want to put this on this one over here, right? Because P0 lives in the catch for that particular CPU, right? I don't want to put it over here on P1, right? This is bad, right? This is good, because that P0 doesn't exist in the catch for that CPU, right? And that could be a little bit of an issue for me. And so that's kind of what sometimes the schedulers are, well, they should pay attention to, but sometimes they don't, right? The idea is that, if your process already exists in the cache for one CPU, it's going to be cheaper basically for you to continue running that CPU for it, right? Even if all of a sudden, this process 1 is free, I mean, I could start up P0 on that one, but I'm going to have to pay the cost of moving stuff from that first catch, right, over to this catch over here. I have to do that move, right? So I have to do two things instead of one. So that's going to be problematic. Ideally, what we want to do is basically have the same process running the same CPU over time, because then I can keep all the data for that one process in that one CPU's cache, right? And that's kind of the ideal, and that'll be kind of the most performance. Well, it's the way I want to go in terms of performance. One way I can do this, right, is basically for something called process affinity. And basically the idea there is that I can mark in my operating system that this process belongs to the CPU, right? So I might say, P0's, affinity, is CPU 0. And what that would imply is that the scheduler's job is to keep that process on that one CPU, right? So that's what we call affinity. And if you even go into your operating system, if you go into Windows, you can usually bring up Task Manager, and you can actually right-click on a process and do something like set affinity and say you run on this processor and this processor only. And if you do that, right, you're kind of helping the scheduler. You're making it so you basically never have the issue where you have to migrate stuff from one cache to another, right? You don't have to worry about that. You just have the ability basically to enforce that one thing to be there, so that you kind of get that you basically are allowed to reuse the cache. Another term here is called cache locality, right? So it's like, well, this data is local to the CPU, right? So we want to basically kind of keep that process running on that CPU where the data exists. Okay, so a few more ideas for you guys. I'm going to talk a little bit about the SMP architecture a little bit here. So this is just kind of a note about load balancing, right? So the idea is I have multiple CPUs running. I all want them to basically be active at any given time. I don't want one CPU to be active while another two are idle, right? They should all be active if there is stuff to do, right? That's what we call load balancing. And we've actually talked about that in terms of threading already. But again, the idea kind of applies to the CPU themselves, right? The hardware themselves. Now, when we do load balancing, generally it's going to be an issue when we have individual queues for processors. So individual processors have this idea of, oh, I want to run this, this, and this, right? That's where we get issues of balance, because what happens is that one process, maybe gets queued 5 drops, another process gets queued 5 drops. While one of those processes ends up going through its queue really fast and it's left basically with nothing to do, right? That's a problem, right? That's a load problem. And so we need some way to address that. Now, if we have one overall global queue that everybody pulls from, generally it's not an issue, because it's like, well, I do one thing, then I go to the global queue, do it, go to the global queue, do it, go to the global queue. I keep on doing that again and again and again. And that global queue is basically just a pool that anybody can pull from any given time. So generally, the load balancing is fine there. It's only when we have a separate queue for each CPU that this is an issue. Now, when we have an issue, right, we can kind of fix it two ways. We have either the idea of push migration or pull migration. In the end, they're the same thing. The idea, right, is I need to migrate a task. So if I am, say, on a CPU that has, I have basically nothing to do, right? I might do something like a pull migration, right? So I might pull something from another process, right? That's if I'm, basically if I'm responsible for it, right? If I'm saying that I, need some more work to do, I do a pull migration to get some more stuff. If maybe I have too much work to do, right, then I do a push migration. So I have 20 tasks, and I see everybody else has only a couple. What happens is I want to basically push some of those tasks to a different CPU, right? So that's what I call push migration, right? So they're both solving the same problem. It's just kind of who's directing it, right? Is the person who's underloaded directing it, right? Are they doing a pull, or is the person that's overloaded doing it? Are they doing a push, right? So it's kind of coming from two sides there. All right, so some final notes here about the idea of memory stalls. You guys have probably already seen this in a previous course, but just as a kind of a reminder / refresher. Basically, the idea of a memory stall, right, is I have my program running, right? So my program is running, right? It's doing some computation, right? It's doing some CPU stuff. All of a sudden, it requests something, right? Maybe it's some data for processing. Maybe it's another function. Point is, it needs to jump out to the RAM, right? Jump out to the hard drive, whatever. Basically, it needs to pull in some more data. It can't do any computation. That results in what's called a memory stall, right? So I'm accessing memory. It's not there. I need to load it, and I can't do any computation until I've done it, right? And so if I look at basically the lifetime of a program, over time, what happens, right, is I'm running stuff, right? I have a memory stall, running stuff, memory stall, I'm running stuff, memory stall, right? I kind of alternate or interleave, right, my periods of being able to do stuff with the, basically me asking for more to read something from memory, right? Those become interleaved. This is kind of bad because it's only this underlying time here that the CPU is really active, right? The other time is kind of idle. It's waiting, for that memory to be accessed so they can actually get on with its computation. So this we want to kind of prevent, right? We don't want to have a whole lot of memory stalls in our program. Now, if we want to address this, one way we can basically do it is by saying, okay, you know what, I'm going to kind of virtually have multiple threads on the CPU at the same time. So I'll have basically 2 programs running. Each program will have some stuff to do. So program, is running, right? First thread is active. It does some stuff, right? And then it stalls out because it makes a request for something. When it stalls out, you make that request kind of, asynchronously. And then the other thread you have running, it gets to go and it gets to do stuff. Eventually, it's a memory stall. And let's say it hits a memory stall, then you can go back to the first one and it can do computation, and then back to the first one. So, right, so basically you end up interleaving the different inputs, right? So or the different threads, right? So each thread kind of takes turns, right? Does some computation, then once it stalls, it lets somebody else run, right? And then once it has its data, it can go back and run. So you basically are canceling out, that time you spent wasted on your your memory stalls. Instead, what you have is kind of one continuous thing here, right, where you're always doing some CPU work. So that would be ideal, right, if we're always kind of active, right? We're never having downtime due to memory stalls.